What's happening, guys? This is the next installment in this exciting series of mechanics. I really do hope you're enjoying it. I hope you are enthralled and riveted and excited and fascinated and enlightened by mechanics. Okay? We are carrying on with chapter 4.3, moment of a force, vector formulation. Okay, so I really encourage you to go and watch the previous video so that you get a nice foundation. The previous chapters were moment of a force, scalar formulation. Okay, now as you can see, I haven't done 4.2. 4.2 you must go and read up on. It's the cross product. Okay, the cross product is crucial. I'm going to basically just look at the application side of the cross product, but you have to go and study chapter 4.2 on the cross product. The basic idea, guys, moment of a force, scalar formula, well, how about we just talk about the scalar formulation? What do you recall in chapters 2 and 3 is that when we were working in two-dimensional space, we could leave our forces in scalar form, okay? But when we moved into three-dimensional space, it was extremely helpful and possibly the only way to solve problems in three-dimensional space. We needed to convert it into Cartesian vector form, okay? So what do you even anticipate when we say vector formulation? Well, you anticipate, if we say we're going to formulate everything in vector form, then you anticipate that we're going to start working now in three-dimensional space. Okay? So that's the basic idea that we need to understand. So what do we have here? Remember that what we had for the scalar formulation was MO, the resultant moment about, or the moment about O was equal to F times D. And what do you see here? We see R cross F. MO equals R cross F. Okay? So, in two-dimensional space, our moment was equal to F times D. Okay? And again, we use the right-hand rule. We're always using the right-hand rule. Okay? Whether we are in two-dimensional space, three-dimensional space, we are always using the right-hand rule to determine our direction. This was our magnitude, F times D, and our direction was based on the right-hand rule. If we had a point there, and there was a force there, it caused a clockwise rotation about the point O, then we knew that we had a magnitude here, but the moment was given as a negative because it is clockwise, and what we said was anti-clockwise is positive. Now, when it comes to three-dimensional space, okay, we are actually this vector formulation can obviously be applied into two-dimensional space. But just as we saw in chapters 2 and 3, when you're in two-dimensional space, it is easier and simpler and quicker to just leave things in scalar formulation, right? Although you can convert to vector formulation and solve it, okay? But when it comes to three-dimensional space, vector formulation is perhaps the only way to solve the problems, okay? So in three-dimensional space, we want to convert into, we essentially want to calculate our moment using vector formulation, okay? So what this means is in vector formulation, this is going to equal R cross F. Now this is something called the cross product. What is the cross product? It is when I multiply two vectors with each other and I get a vector. Remember the dot product? The dot product was I multiplied two vectors and I got a scalar. The dot product was vector, one vector and another vector, and when I did A dot B, I got a scalar, right? That's the dot product. you need to go revise what the dot product does, okay? But the cross product, I say one vector R cross another vector F, and out comes a vector, okay? Now, before we go into details of what is R and F, etc., the first thing that needs to just stick in our mind conceptually or intuitively is that we use the cross product to calculate our moment when we have our force and our moment arm in vector form. Okay? When we carry out the cross product, we are going to get a vector. What does this vector mean? This vector will have two components. Can you even possibly imagine what these two components will be? One will be a magnitude, and what do you think the other one will be? It will be a direction, obviously, right? What is the magnitude of this vector, MO, which is R cross F? The magnitude will just be the magnitude of the moment, right? The magnitude of the moment. And now, what is the direction? If you've watched the previous videos, you will see how much emphasis I put on the direction. Let's talk about the direction of this vector. Remember, we use the cross product. Well, we'll get into an actual example, but I'm trying to give you an intuitive understanding. We have these two vectors. The one is your moment arm R. The other one is your force. Okay? We'll go into this R a bit later. We carry out the cross product of these two, and we get a vector. This vector has a magnitude and a direction. The direction, okay, if you use the right-hand rule, again, let's have a look here. There's that lovely little hand. Do you see it? Let me just get my pen. There is our lovely hand. Okay? The direction of our moment, remember in the previous videos, I hope you've watched the previous videos. What I said was, we calculate a moment, we calculate the direction of the moment using the right-hand rule. The curl of our fingers will give us the direction, the sense of direction, around an axis, which is our thumb. Okay? So the direction of our moment will be something that is in the direction of the thumb. Okay? And the fingers will give us the sense of rotation about the axis, which is along the direction of the thumb. Alright? So that is essentially what we will end up with. So we need to remember that we are carrying out the right-hand rule. Okay? Now, another interesting thing about this vector is, as I mentioned in the previous videos, this vector is perpendicular to vectors R and F. Remember, in the two-dimensional space, I said that your thumb is perpendicular to F and D, the plane that F and D are in. Well, this vector is exactly the same. It is perpendicular to the plane of R and F. It's perpendicular to the plane that R and F are acting in. Okay. So now, what is R? What is R? R is a position vector. Okay, so remember that in two-dimensional space we had a force and a distance, D. So in two-dimensional space, if there was my O and there's my force F, remember I drew the line of action like that, and I calculated a perpendicular distance, and that was my D. My magnitude was FD, and then was that going anti-clockwise or clockwise? It was going, in this case, anti-clockwise, so that's a positive. Okay, that is my scalar formulation. In three-dimensional space, there's my point O, and there is my force in vector form. Okay? Okay? Now, how do I determine R? Guys, very important. I want you to repeat this to yourself 10 million times. No, 20 million times. 20 million times. How do I determine my position vector? Remember in scalar formulation, two-dimensional space, that's how you got your moment arm. Right? In three-dimensional space, vector formulation, I want you to memorize this, repeat it 20 million times. Your position vector R is equal to any vector, any position vector, any position vector, any position vector, okay? Any position vector from point O to any point that is along the line of action of F. Any position vector from point O to any point along the line of action of F. Have you guys got that? When we are working with our vector formulation and we're trying to calculate our moment, we need a moment arm. Remember, this is the vector formulation of the moment arm. It is a position vector. In scalar, it's a moment arm D, but in vector formulation, I need a position vector from the point O to any point along the line of action of F. Okay? Well, we'll see an example and then you'll see what we mean by this. Okay? So that's what R is. R is any vector, any position vector from point O to any point along the line of action of F. Okay? So that's what R is. It's a position vector from point O to the line of action of F. Okay. Now, how do we actually calculate the cross product? How do we calculate the cross product? Again, what does the cross product do? The cross product is vector multiplication that allows us to calculate the moment of a force. It allows us to calculate the rotational effect of a force. So let's say our force in vector form was equal to 2I minus 3J plus 4K. And that's in Newton. Let's just practice something here. And then we calculated a position vector from point O to we found any point. We found a point along the line of action of F. And this was equal to I minus J plus 2K. All right? Just making up some numbers here. So now we need to carry out the cross product of F and R in order to calculate the moment. Now what is crucial to see, guys, is that R cross F is not equal to F cross R. It's very important that we have the correct order here. Okay? They're not, I think the word is commutative. They're not commutative. These two will have exactly the same magnitude, but they will have the wrong direction. Okay? So what do? You need to go study the cross product. But the resultant moment equal to R cross F is equal to the determinant. So what do? We go I, J, K. We put in R in the first row, the components of R. So we've got I minus J plus 2K. So we put in 1 there because it's 1I. We put in minus 1 there because it's minus 1J. And we put a 2 in there. Okay, because it's R, X, RY, RZ. Then this next row we put in the components of F. 2, minus 3, 4. And that is now something called, now we need to calculate our determinant. Okay? So this you just need to practice. Again, as I mentioned in class, this is not a maths course, and you will do something called linear algebra next term, next semester, which will give you more insight into what we're doing here. Nevertheless, this is the cross product. How does it work? Remember, what we're doing is we're multiplying these two vectors with each other. Don't lose sight of what we're doing. We're multiplying these two vectors with each other using something called the cross product. How does it work? We start off by crossing out that column and that row, and we say that times that minus that times that. We cross these out, and we're left with these four numbers, and we say, we open up, we say I, because we're crossing out the ith column. I don't know if that's the right thing. That's not right. We're crossing out the I column. The I column. Crossing it out, cross out that row. We're left with these four numbers. And we say that times that minus that times that. Okay? You need to go and study. Go and have a look at this section here, where it speaks about the cross product. Okay? First vector, second vector. And whatever's remaining, okay, you cross the first column out, you cross the first row out, and you've got this kind of pattern here that you say that times that minus that times that, that times that minus that times that. So it's I, and then you carry out this pattern of multiplication. That times that minus that times that. You close the bracket. Then, and please don't ask me why, this is not a maths course, then you put in a minus sign, J, and you cross out the J column and that row, and you're left with these four numbers. That times that minus that times that. Okay? Then you cross out the K column and the first row, and you're left with these four numbers. You go that times that minus that times that. Okay? Guys, it's really just practice. And what this does is it helps you calculate something called the determinant. Okay? So let's do a little exercise here. So we're going to have minus 1 times 4. So it's that times that minus that times that. Minus 1 times minus 4 minus 2 times minus 3. Close bracket. Now remember, the second one is a minus. Don't forget the minus. So then we say J, and we open up the bracket. Now we cross this out, and we cross that out. Now we're left with these four numbers here. Da, 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 da. So it's that times that minus that times that. 1 times 4 minus 2 times 2. 2 times 2. Okay? Then plus K, open bracket, cross out this kth column, not the kth column, the K column, K, and we cross that out. Okay, then we're left with these four numbers, so it's that times that minus that times that. So 1 times minus 3 minus 1 times 2, close brackets. Then, if I can try to find my calculator. Okay, I found it. So, what do we have here? We have minus 4 plus 6, if I'm not mistaken. So, minus 4 minus 2 times minus 3. No, we're wrong here. So, 2 times 3 is 6, and that's a plus. Minus 4 is 2i. Okay, we've got 2i here. Then, what is this? We've got 4 minus 4. Right? 1 times 4 is 4. Minus 2 times 2 is 4. So we're going to have 0j. Okay? 0j. Then we're going to have minus 3 plus 2. Right? So it's 1 times minus 3 minus 1 times 2 gives us minus 1k. So minus 3 plus 2 is minus 1k. So this is Newton meter. You've now calculated the moment. Okay, so now that we've done all the maths and we've gotten this answer, we have to ask ourselves, what does this mean? Well, remember what I said to you earlier, that our moment, we use the cross product, R cross F, and it gives us a vector. This vector has a magnitude and a direction. What does this mean? Let's just rewrite it. 2I minus K Newton meter. That's my moment in Cartesian vector form. So what is the magnitude of this moment? The magnitude will be 2 squared plus minus 1 squared square root. That is the magnitude of this moment. So it's going to be 4 plus 1 is root 5. Okay? Root 5 Newton meter. So that is the magnitude. That's the size of my moment. Okay? But then, what is the direction? Let me just rewrite it. I've got 2I minus K. Guys, please, I'm begging you to try your best to understand what we mean by direction. So we calculated the magnitude was root 5 Newton meter. Okay? So the magnitude of MO, okay, 2 squared plus 1 squared. Is that right? 4 plus 1, yes. Now the direction. What is the direction? Well, remember, I said to you that this is a vector. R cross F. MO equals R cross F gives me a vector. There's my vector. Okay? And this vector has a magnitude and a direction. We've calculated our magnitude. Now our direction. Guys, it's a straightforward vector. If there's my y, x, z, and there was my point O, right? My point O, our rotation. Then, in this case, I go 2 in the x direction and minus 1 in the k. So I've got now, there's my vector, there's my MO vector. What does it mean? It means I put my thumb, remember, right hand rule. I put my thumb in the direction of this moment and my fingers curl around this axis. Okay? And so the direction that my fingers are curling gives me the sense of direction of this moment. I hope you can understand that, guys. When we're talking about the direction of a moment, we use the right-hand rule. My thumb is the axis that is perpendicular to R and F, and it is the axis. My thumb goes in the direction of the axis about which the body is rotating. Okay? So if this is the axis, my thumb goes in the direction of that axis. My fingers curl around. I hope you can see that. My fingers curl around this axis. My thumb goes in the direction of this axis, and my fingers curl around. The direction, the curl of my fingers gives us the sense of direction, of rotation. Okay? It's curling, it's going around there. So this force and this force that I made up over here and this position vector here gives me a resultant moment that is, the direction is in this direction, and my fingers curl around that axis. So that is the sense of rotation based on this example that I made up. Okay? So I hope that you're getting a bit more of an intuitive feeling. We will do 1 or 2 examples in the next video. Thanks, guys. Cheers.